Hey there, welcome to another edition of Mr. Weis Solves an Old AP Problem. So today we're working on AP Calculus BC 2007, number 3. The setup for this problem is kind of cool. It's a polar function sort of situation. They give us two polar functions, r equals 2 and r equals 3 plus 2 cosine of theta. They even provide us with a graph in the xy plane of these two functions, though they don't tell us which one is which. They also give us some interesting information about the angle of intersection of these two, which is nice of them. They tell us that this intersects at 2 pi over 3, and that this intersects at 4 pi over 3. And what we are interested in doing is finding the area enclosed by both the black graph and the blue graph. So all of this area that you see right here is what we want to find. That's what part A asks us to compute. Part A wants us to find the area enclosed by the circle, which is r equals 2, and the cardioid, which is r equals 3 plus 2 cosine theta. I don't believe they provide a scale on their axis, but you could figure out what this is. This is a circle of radius 2, so 1, 2. If you were to plug in theta equals 0 into this, you would get that r equals 5, so 3, 4, 5. That's the biggest r ever gets for the blue curve, which is this one, the cardioid. You can see that when theta equals pi, cosine of theta is -1, so we get 3 minus 2, which is 1. So this comes in, and the smallest r ever gets is 1. This graph would be actually very easy to draw by hand because there's no negative r's that we have to worry about here. So I'm going to break this integral up into two pieces, and in fact I'm going to use a fair amount of symmetry. So for the first piece of this area, I'm going to realize that I basically want, as theta goes from 0 all the way to the angle 2 pi over 3, basically all I want is the area of this sector of a circle. So that's actually all this is. This is just a sector of a circle. And I happen to know the formula for the area of a sector of circle, and you should too, because basically that's the formula for the area of a sector of circle that gave us the integrals for computing areas of polar graphs. So this angle right here is the one that is of interest, because I'm going to do a lot of doubling here. So I see that that's pi over 2 plus another, that angle is just 2 pi over 3. So the area of the orange bit, which I might draw like this, it's just a sector of a circle, this area is equal to 1/2 r squared, r is 2 in this case, so 2 squared, theta. Theta is 2 pi over 3. That's the area of that bit. Okay. After we hit the angle of 2 pi over 3, then I'm shooting out from the origin, hitting my blue curve like so, as theta increases, all the way till I get to 2 pi. For that area, we will in fact need an integral. And that area kind of looks something like this. Something like that. Oh, sorry, that should be a sort of a straight line shooting up like that. So that's the other piece that we're trying to find. And so here we go. For that part, that's going to end up being plus 1/2, because every polar area comes with a half. The integral from, we're starting at 2 pi over 3, and we're going up to pi of r squared. R in this case is the function 3 plus 2 cosine of theta squared d theta. And then of course, importantly, let's not forget, I want to double all of this. And I want to find 2 times all of this. So this is a calculator problem. You're going to plug this into your calculator. Not that you couldn't do this by hand. It is totally possible to do this by hand. You'll require the power reducing formula to take this integral, and that's all that would be necessary here. But I'm going to go ahead and find it, find all of this. So let's see. Do it all in one big fell swoop. So actually, I'll distribute the 2 into both parts here so that I don't have to deal with the 1/2. So it looks like I'm going to end up getting 4 times 2 pi over 3. Okay, plus the 1/2 is gone, so the integral, math 9. I'm doing the integral from 2 pi over 3 to pi of the quantity 3 plus 2 cosine of x squared dx. And I just want to make sure that I'm in the right mode, so I'm going to go in and check I am in the right mode. So then I'll just hit enter, and I get 10.3704. This is approximately, the area is approximately 10.370, and that is my final answer. Okay, so here we are doing part B of the 2007 number 3 AP Calculus BC exam. We're dealing with this function that's these set of functions actually, though in part B we're only going to be dealing with this one. It is a polar function given by the equation r equals 3 plus 2 cosine of theta, and it makes this blue cardioid shape that you see here. So question B is kind of interesting because now question B is going to talk about a particle that's moving along this curve as time varies. And I'm going to read it out loud and then talk a little bit about what it means. So it says a particle moves with a non-zero velocity, that's the direction and speed, along the polar curve, r equals 3 plus 2 cosine of theta, and has position x of t comma y of t at time t. So at any moment in time, we could talk about where this particle is. So I can put a little dot right here, and I could name that point x of t comma y of t. That is the position of the particle at time t. Now here's the deal. They tell us that when theta equals 0, which is point when theta equals 0, that's when we're all the way out here. Boop, 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 boop. That's theta equals 0. Its position, that's where it is at time 0. So this point right here happens to be x of 0 comma y of 0. That's its position at time 0, which by the way we can easily find by just thinking about it actually. At theta equals 0 we know that r is 0, and so we know that, at theta equals 0 we know that r is 5, and so its position at time 0 is 5 comma 0. So this has a lot to do with converting things into parametric equations and stuff, the stuff we did in order to do calculus ultimately on polar curves. Now, it keeps on going. It says that the particle moves along the curve so that dr dt is always equal to dr d theta. So, what this means is that the instantaneous rate of change of the distance from the origin, remember r means the distance from the origin, that means the distance from the origin. So dr dt is the rate of change of the distance to the origin. So you can see that as the particle moves around the curve, you should actually be able to see that the distance to the origin is in fact getting smaller and smaller and smaller and smaller and smaller and smaller and smaller, and then bigger and 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 bigger as it moves around this curve. Well, they're telling us that you can figure out what the instantaneous rate of change of that distance to the origin is by just finding dr d theta. Ultimately, what this is really just saying is that the parameter of time is actually just theta. At any moment in time, you can look at the angle that the particle is at, and that'll tell you where it is, that'll tell you its speed, well, it'll end up being able to tell you how fast the r is changing, etc. So, it asks to find, what we want to do is find dr dt. Find dr dt when theta equals pi over 3. And interpret the meaning of this thing. So pi over 3 is right here. The angle pi over 3 is kind of like right there. I don't know, my graph might not be perfect, but there's the angle of pi over 3. What we're going to find is dr dt at theta equals pi over 3. But remember, dr dt is really just dr d theta, so basically all they're asking us to do is find the derivative of this with respect to theta and plug in pi over 3. I could use my calculator to do this. I believe the answer on according to the College Board, they just used their calculator, and you probably should too, but I'm going to really quickly just find it. So dr dt equals dr dt equals dr d theta, which equals, if I take the derivative of this with respect to theta, I think we just get -2 sine of theta, which I can now plug pi over 3 into. So dr dt at pi over 3 for theta, which is actually just t, is equal to -2 sine of pi over 3, which I believe ends up just giving us -√3, which is approximately 1.732. Let's just check that. Second square root of 3, 1.732. Now they want us to interpret this, so you're going to write a little sentence that says, at the moment in time when the angle happens to be pi over 3, the instantaneous rate of change of the distance to the origin is -1.732. So what does this mean? This means that at this moment in time, when the particle happens to be right here, if you were to increase the angle by 1 radian, the r would change by approximately, the distance to the origin would change by approximately -1.732. Now this is actually not very good estimate because 1 radian is actually incredibly huge. Increasing r by 1 radian ends you up over here, and so all the way at about 2 pi over 3. So I don't suspect this would be a very good estimate for just 1 radian, but there you have it. Okay, here we are doing the final part of the 2007 number 3 AP Calculus BC exam. We're dealing with this polar curve r equals 3 plus 2 cosine of theta, which describes this cardioid that you see here. And in these last two parts, the deal is there's a particle that's moving along this cardioid. It's actually moving in this direction counterclockwise. At any moment in time, its position x of t comma y of t is actually just equal to x of theta comma y of theta. And so in other words, this curve is parameterized by the angle theta that it makes. And we did some cool stuff by looking at dr dt and dr d theta. In this part they want us to note that similarly to the thing with dr dt, note that dy dt is the same thing as dy d theta. So the rate of change of the y coordinate of this particle at any moment in time is the same thing as the rate of change of this y coordinate at any angle theta with respect to that angle theta at any angle theta. Basically because t and theta are playing the same role. Now what do they want us to find? They want us to find and again interpret what does dy dt equal when theta equals pi over 3. So theta equals pi over 3. Okay, this is actually a pretty straightforward problem. So the thing that we have to remember is there is a way to get from polar curves to parametric curves. It was the big way that we realized how to find things like arc length, how to find slopes of tangent lines to polar curves. It's literally what we did. So the way this works is you remember that actually y equals, in a polar setting, y equals r sine theta, x equals r cosine theta. So that's actually what y of theta is. That's actually y of theta. So therefore, and x of theta, by the way, is r cosine theta. R in this case is 3 plus 2 cosine theta. So in other words, it equals 3 plus 2 cosine theta times sine of theta. And what we're being asked to find here is dy dt, which is dy d theta. And again, I could use the calculator to do this, and in fact the answer has you using the calculator, and you certainly should on the AP exam. But whatever, we can easily find this derivative. It's not very hard, so I'm just going to go ahead and find the derivative. So I'm going to start by distributing the sign in there. So I'm going to write this as 3 sine of theta plus, and then actually I'm going to remember that this is 2 cosine theta sine theta, which is the same thing as sine of 2 theta. Sine of 2 theta equals 2 sine cosine. So that makes derivatives easier. If I were solving equations involving y, this is not a good thing to do, as I think we saw in this unit. But when we're taking derivatives, this is fantastic. So dy d theta is just going to equal 3 cosine of theta plus, and now I have to use the chain rule, so this is going to be cosine of 2 theta times 2. Cool? So the answer, dy dt at theta equals pi over 3, is simply going to equal 3 cosine of pi over 3 plus 2 cosine of 2 pi over 3. So let's see, cosine of pi over 3 is a half, so this equals 3 halves plus, and then cosine of 2 pi over 3 is negative 1 half, so minus 1. So I believe the answer is 1/2. Cool. Now they ask us to interpret what this means. Well, I think the main important fact to realize is, unlike dr d theta, which we found in the last part, dr d theta was negative at this time slash angle. And what that meant as at that time slash angle, the distance to the origin was decreasing. This particle is actually getting closer to the origin as the particle moves along this curve. But dy dt is positive at this time slash angle. So interestingly, even though the particle is getting closer to the origin, at this moment in time, its y coordinate is actually getting bigger. So the y coordinate is actually getting further from the origin, even though overall the particle is getting closer to the origin. So that's what's happening. And I think the sentence you want to say here is that at this moment in time slash angle, the y coordinate is increasing. That's y coordinate is not the distance from the origin. The y coordinate is this part right here. And that is actually getting bigger. You can kind of see that. It's not getting bigger by very much. My picture may not be perfectly drawn to scale. It's not getting bigger by very much, but the y coordinate is getting higher. The x coordinate, of course, is getting smaller. And it is for that reason that essentially we end up getting closer to the origin at that point. And that is my long-winded final answer.